Okay, so we want to finish up Chapter 8. As we go through Chapter 8, we're going to continue working with some information that we already understand and hopefully have a grasp of. One of those first things we're going to recognize is that there is, we talked about torque. We talked about how it's a force applied at a distance from the radius of rotation. And what we have to recognize is that the bigger the torque is, right, because torque is force times the radius times the sine of the angle between them. If we talk about this, if we have a big force, which means we have a big torque, we would expect the rate at which the wheel or object accelerates to be faster. Whereas if I just give it a little torque, we'd expect it to have a small amount of acceleration in terms of angular quantities. And so what we learn is that the alpha, our angular acceleration, is proportional to what we call the net torque or the total torque. And there's this relationship that must exist between how quickly something is accelerating and rolling over itself and how much torque is applied. And so when we look at this formula and we talk about how torque and acceleration are related, we recognize that the mass has a big part to do with it, but also how far out that mass is. Because if the mass is located towards the center versus located out on the edge, there's going to be a different sense of how hard it is to roll something. And so we have this formula here, that our torque is equal to the mass of the object times the radius squared times alpha. Well, this mr squared, we have to recognize that when some mass is, if you think about this wheel, this circle, if this is full of mass, okay, this is a full solid tube, some of the mass is out at the radius, but some of the mass is also very close to the center. So we have to recognize that it's not a perfect distribution. And so we have down here this concept of the sum of mr squared, which means that we have to recognize that there's sort of a calculus approach to this, where we're talking about all of the infinite mass, or all the little particles inside, which would take us forever to count them all up, all the little atoms, figuring out exactly where their stuff's at. I mean, it would take us forever to do this calculation. But using some calculus, we can do some summations. And what we find out, okay, or essentially come to grips with, is that the moment of inertia, which we're going to use a capital I for that, is equal to this summation. And so in the formula, we now have this simpler, smaller looking version, that the torque, or the sum of the torques, if you add up all of the forces applied at a distance that cause rotation, it will equal the moment of inertia times the angular acceleration. Now, why this matters is because the moment of inertia is unique for different shapes, and so depending on the shape, the same torque can cause different accelerations. So we want to know more about this moment of inertia. And on page 208 of the textbook, we're going to find out a lot of information about it. So we keep going. Essentially, when we look at different objects that roll, the closer the mass is to the center, okay, because it's mr squared, the smaller the r, the smaller the moment of inertia. And if we look at this, if a moment of inertia goes down, that means that alpha will go up. So we want something to accelerate quickly. We want the moment of inertia to be low. Or we want all of the mass that we can manage to be close to the center. So let's take a look at some of these formulas and how they are applied. We're really only going to look at a few of these. We will do a thin hoop, which this thin hoop thing we're going to treat the same. A solid cylinder and a uniform sphere. These are the three that we'll talk about in class pretty consistently. As a thin hoop, that means all of the mass is out on the radius. Okay, so if you think about it that way, all of the mass is out on the edge. You could think of this kind of like a bike tire. I do understand that a bike tire has mass in the middle, its axle, and the spokes, but for the most part, a traditional bike tire most of its mass is going to be out on the rim and with the tire and all that stuff. So typically we're going to say that's where our mass is applied, and so our moment of inertia, the I in the equation, would be mr squared. Now, interestingly enough, when we fill it in and we make it a solid disk or a solid cylinder, you'll hear the word disk used, because the mass is creeping its way in towards the center, right? It's not all out on the edge, but because of how it's distributed, our moment of inertia is dropped in half. So now the moment of inertia of a solid disk is only half because so much of the mass is concentrated towards the middle. And an even better, version of that would be, what if we could approximate it down to a sphere? Because then if you think about the sphere rotating about this axis, right? There is some mass that is actually on the axis, not just the center point, but like there's quite a bit of mass that's in that first little bit of space right close to the axis. And so all this mass, man, that's close. It's not going to affect the rolling. It's not going to be as big of an impact on the moment of inertia as the mass that's out on the edges there. And so here the moment of inertia is dropped even more down to 2/5 of mr squared. There are lots of other applications, and if we wanted to, we would really approach these individually as calculus problems. Because what happens if you have something like a bike tire, where it's not all on the outside, it's also not evenly distributed along the way. We're going to have to become more exact, and if we want to be super exact, we'd have to use some calculus. But for us, we're still in high school, so I think we'll just deal with the formulas and use them the way that they are. But the moment of inertia is something that we will calculate a few times, and if we want to know its unit, mass is kilograms, radius is meters, so it would be kilograms times meters squared would be the unit for a moment of inertia. That's going to allow us to solve a lot of problems using torque and alpha, our acceleration. The second formula we need to talk a little bit about is recognizing the fact that while a ball or tire or round object rolls, even if it doesn't move horizontally across a surface or doesn't move through space, it still has kinetic energy. It's still rotating, and therefore there must be a distinction between translational kinetic energy, which is the side-to-side movement, and something that rolls. Because if it's rolling and moving, those are two different types of kinetic energy, but they still need to be accounted for. And so if you can imagine this ball rolling down the hill, if I wanted to talk about its potential energy at the beginning here, right? Potential energy up here, at the bottom, not only would the ball be moving down the inclines, there'd be kinetic energy, but there'd also be rotation of the ball. And so that would be kinetic energy in the rotational meaning. And so we would have to talk about rotational kinetic energy and translational kinetic energy as two separate things. But the nice thing is, when we're talking about rotational kinetic energy, there's a very simple formula that looks a lot like the one we know for regular kinetic energy or translational. Here, the rotational kinetic energy is 1/2 the moment of inertia times the angular velocity omega squared. So let's recap real quick. We've learned that torque is equal to I alpha. We have a whole bunch of formulas for I equals. That's on page 208. Okay, did that kind of weird. Okay, and then now we have that rotational kinetic energy will be 1/2 I omega squared. Keep in mind, if we talk about total kinetic energy, we also have that 1/2 mv squared, right? And so those are things to consider as we look forward. I think this is the last topic we're going to have. Pretty sure it is. It could be wrong. But this last topic that we have, angular momentum. So just like linear momentum is conserved, whether through a collision or through an interaction, we can say the same thing is true for angular momentum. Now you have seen this in real life. You've probably experienced it in real life. If you watched an ice skater that spins in a circle, pulls their arms in, and suddenly they spin faster, that's because they've changed their moment of inertia, but their momentum, their angular momentum, is being conserved. So we have, in this section, we're going to talk about angular momentum, and we use the capital letter L for angular momentum. And so where we had straight line momentum, P equals mv, here we have angular momentum, L equals I omega. So that moment of inertia really matters. And if the moment of inertia changes, it will force the angular velocity to change, because at any point, L1 must equal L2, meaning we have a conservation of that momentum. Now, doing some fun substitution and analysis of torque equals I alpha, we can also end up with this formula, where if we want to know how much momentum change there would be, because there is a possibility to change momentum by applying an external force, or in this case, an external torque. Think of a merry-go-round, okay? You get on the merry-go-round and get it spinning really fast. Will it spin forever? The answer is no, because friction will slow it down. Or someone else can come and slow it down. So angular momentum is not conserved when there are those non-conservative forces from the outside. But if I were to stay in a frictionless environment, my momentum would absolutely be conserved. And this is really important for space travel. If we give a spin to a rocket ship, okay, out in space, if we can get it away from other objects, it will continue to spin forever. And if we extend arms out on that, we've changed its moment of inertia, and therefore it's going to change the way it rotates. Change the speed at which it rotates, it's going to make a difference. So understanding that momentum, angular momentum is conserved is really important. I think we're good to finish up and look at a couple of homework problems. You'll notice in this one I did tweak the homework assignments, so kind of look for that. I think here we start here in 27. Determine the moment of inertia of a 10.8 kilogram sphere with a radius of 0.648. You know, the moment of inertia, I, equals, in the case of a sphere, 2/5 mr squared. Now, if you don't know that, you go to page 208 of the text and you can find the table that has this. So it'd be 2/5, your mass is 10.8, and your radius is 0.648. Don't forget that that gets squared. And whatever that comes out to will be our 1.81. Pretty straightforward to calculate the moment of inertia. Whoops, I forgot. Get rid of that real quick. All right. Let me go down. Let's find some other stuff that you guys might need a little bit of help getting going. Rotational kinetic energy. I really like these. It talks about the moment of inertia. That's our I. How much energy is required to bring it from rest to rotating. So a centrifuge motor, you know, it spins things in a circle. We use it to like separate different fluids or different materials. Heavy materials go to the outside. Lighter materials come towards the middle. And so when we're talking about spinning a centrifuge up, what we're recognizing is that the initial angular velocity was 0, but the new angular velocity is whatever 8250 is in radians per second. So 8250 RPMs needs to be converted to radians per second, which is times 2 pi divided by 60. That'll give us a new number for our radians per second. We want to know how much energy is required. Well, it went from 0 rotational energy to a whole bunch of rotational energy. And when you figure out how much rotational energy there is at the end, that should tell us how much energy was put into the system. And that's just 1/2 I omega squared. Well, once you get omega to be in radians per second, that's an easy calculation. And then they gave you the moment of inertia. They gave you I. So it's pretty easy to calculate. We skip 44, 45. Keep in mind, on 45. The ball is rolling down the lane without slipping. It has rotational and kinetic energy, rotational and translational. So one of the things that gets people into trouble is we're told that it's going at a velocity of 3.3 meters per second. That doesn't tell me how fast it's rotating. And so I can find the 1/2 mv squared right now. I've got the mass, it's 7.3 kilograms, I've got the velocity, but what I can't find is I omega squared. Now I, it's a sphere, right? A bowling ball is a sphere, so that's 2/5 mr squared. Do you have the mass? Yes. Do you have the radius? Yes. But we still don't know how fast is the ball rotating. What's its radian per second rotation rate? Well, remember there is a formula that attaches velocity to angular velocity. And that relationship between the two of them, I want to make sure I don't botch this. So let me make sure I get it put in the right order. V equals R omega. That's the relationship between velocity in a straight line and the rotational speed of the ball as it rotates around. This formula should allow us to find omega and plug that in there. And once we know that, we're good to go. So I'm going to leave that to you. Question number 5 or 55, just kind of, well, I think you might not be doing 55, but some of these other torque problems and moments of inertia. Okay. Angular momentum of a 2.8 kilogram uniform cylindrical grinding wheel with a radius of 18 centimeters when rotating 1500 RPM. Well, the angular momentum is L equals I omega. Moment of inertia for a cylinder, that would be a solid disk, which is 1/2 mr squared. And omega, they gave us the RPMs. It's 1500 times 2 pi over 60 to get it into radians per second. That's a pretty easy calculation to make. But then the second question, how much torque does it take to stop the thing in 6 seconds? Well, one of the definitions we have was change in momentum. I don't want to say it wrong. Change in momentum over change in time would be our torque. So one of the definitions we came across, or formulas we came across with, was that torque will create a change in momentum over time. Well, if we know how much momentum it had to begin with, angular momentum, and we know it's taking 6 seconds, we can figure out how much torque it would take. Now keep in mind, it is negative because you're trying to remove angular momentum instead of give angular momentum. All right, good luck. We'll see you in class. I know it's a long video, but man, this is physics. It covers a lot, and I know I didn't even get into the details of everything. So we'll see you guys in class.